So this week we're going to be talking about the Grignard reaction in experiment 15. Before we get talking about the reaction that we're going to do this week, let's talk a little bit about the Grignard reagent. You are going to be preparing your own Grignard reagent in this laboratory. And we can generically draw a Grignard reagent as R-MgX, where of course Mg is magnesium, R is any alkyl or phenyl group, and X can either be chlorine, bromine, or iodine. Notice fluorine's absent. Fluorines don't make good Grignard reagents. The fact that you have this carbon-magnesium bond gives it carbanion character. In other words, it's going to behave as if R is negatively charged. So we have a partial negative charge on the carbon and a partial positive charge on the magnesium. And the reason for that is the electronegativity differences. Metals have lower electronegativity values than does carbon. And so carbon's pulling more of those electrons to itself. And so you can think of these as simply, I'm going to put it in quotes, as a real carbanion. They're not true carbanions, but that's how they behave. They do behave as carbanions. And so since we have a carbon with a negative charge, they're going to function as both nucleophiles and as very strong bases, and that has consequences in the reaction as well. So let's look at how we can make some Grignard reagents. So if we start off with bromobenzene, which is the reagent you all are going to be using this week in the lab, you're going to take that, put it in anhydrous diethyl ether. So I abbreviate that as ET2O. Anhydrous meaning no water. And magnesium metal. You're going to mix these together with a single crystal of iodine. The iodine is going to change the color of the solution to kind of a purplish color. You're not using a full equivalent of iodine, and the iodine helps the reaction get started. We won't go into the mechanism of how that occurs, but nonetheless, a little bit of iodine really helps this reaction get started. And once the reaction gets started and you're forming your Grignard reagent, the color of the iodine goes away, so it also functions as an indicator to let you know that the reaction is gone. So if you use a small crystal of iodine and you get this reaction going, you should see that color dissipate pretty quickly. If, however, you're heating your solution for a while and the iodine color remains, you need to get in touch with your TA and have them come over and try to solve the problem because your Grignard reaction is not initiating. We can also make Grignards from alkyl halides. We don't have to have the benzene ring. In this case, we've got bromoethane, again, the same type of conditions, and one can get to the alkyl Grignards as well. It works very well for both alkyl halides and aryl halides, as we call them, for example, with the bromobenzene. Now, Grignard reagents can react with a number of functional groups to give a variety of different types of products. So, for example, if we're starting off with our Grignard reagent here that you're going to be using this week, we could react that with ketones, and then after workup, of course, we would end up with a tertiary alcohol. We could react the Grignard with an aldehyde and end up with a secondary alcohol, or we could react the Grignard with an ester, which is what you're going to be doing this week in the lab, and we would end up with a tertiary alcohol. And it's very important here to note the stoichiometry is not 1-to-1, it's 2-to-1. You need 2 moles of your Grignard for every mole of the ester to get to the final product. Okay? Another important point is that Grignards will react with water to give you the reduced compound. In this case, it would be benzene. So if we took our Grignard and we had any water present, we would actually get benzene back. So this is a great way to take an alkyl halide or an aryl halide and get back, removing the halogen and replacing it with a hydrogen. One way to do that is to use the Grignard reaction and then dump it on water. But this also has an important consequence for your lab technique this week. It means that you have to be absolutely sure that everything is dry and ready to go, because even a single drop of water will cause a huge problem with this reaction. A single drop of water is enough to kill the reaction, and so lab technique is very important. So let's see how much water is in a drop. A drop doesn't sound like a whole lot of anything, a single drop, but in fact it's enough to kill your Grignard reaction this week, and here's the calculation to show why. So we know we have 1 drop of water. And we need to know how many moles that is. That's ultimately what we need to know. We know that 1 milliliter is approximately 20 drops. Of course, it depends on the size of the drop, but this is kind of a generally accepted value, 20 good-sized drops to the milliliter. And so we know that we have a milliliter, and we've got 20 drops. Drops cancel, and we're left with milliliters of water at this point. We know that 1 gram of water has a volume of 1 milliliter. That's just the density of water, so that gives us grams of water. And we know that 1 mole of water is 18 grams. So that gives us moles of water. And when we go through and do this quick calculation, we find that we have 2.8 times 10 to the negative third moles of water in that single drop. That's 2.8 millimoles of water for every drop. And it turns out, in this lab, since we're doing this on a micro scale, the bromobenzene that we'll be using to generate the Grignard you're only starting off with 2.5 millimoles. So if you were able to convert every bit of your bromobenzene into the Grignard, you would only have 2.5 millimoles of Grignard. And a single drop is more than that. And that's more than enough to completely quench your Grignard and kill your reaction in that single drop. So it is very, very critical this week that you make sure that all your glassware is thoroughly dried, that you're not getting that glassware near a sink, that no splashes of water are getting into it, etc. We even have to take caution for the moisture in the air by using a drying tube, and your TA is going to show you how to set up the reaction apparatus and dry it properly in the presence of a drying tube to make sure that no moisture from our humid air down here gets down into that reaction flask and causes a lot of problems. So let's look at the reaction mechanism for reacting these Grignard reagents that you're going to be making with the ester that you made last week in lab. The synthetic snapdragon scent is what we're going to be using this week as our ester. And so we've got our Grignard reagent, and we've also got our synthetic snapdragon scent, methyl benzoate, and the pH is just an abbreviation for the benzene ring here. And I've just done that as an abbreviation. We know that these function as good nucleophiles, so this is going to be our Lewis base. We know that esters having the weak pi bond on the carbonyl can function as electron acceptors or as Lewis acids. And so we have a reaction occurring, breaking that weak pi bond. I'm going to draw it like that. This is known as the tetrahedral intermediate, which is unstable, and it will rapidly decompose. Kick out the OCH3 minus as an anion. We end up with that salt as a byproduct. Notice we get a ketone as the first intermediate. However, we know that Grignards do not react with esters to ultimately give ketones. And the reason is the ketone product that we get here is an intermediate, and it's more reactive than the starting ester. So once this is formed, it's going to react first with any remaining Grignard reagent. So another mole of Grignard then comes in. And reacts with the ketone. to give the alkoxide intermediate, which is where we stop until we're done with the reaction and we quench it over a little acid and water. Pour it over ice probably is usually a good idea. So these two benzene rings that I actually draw out come from the Grignards, and the phenyl, of course, comes from the starting methyl benzoate that we started with. And you end up with your triphenylmethanol product. And the important thing to note here in this entire reaction sequence, we're converting an ester ultimately into an alcohol, which is important. But more importantly, we are forming carbon-carbon bonds. In this particular reaction here, we formed a carbon-carbon bond here. And in the second reaction, we formed a second carbon-carbon bond in that process. And it turns out that forming carbon-carbon bonds is one of the most challenging things to do as an organic chemist. But it's very important that we be able to form carbon-carbon bonds so that we can build larger molecules from simpler molecules. Much of the reactions that you've learned in lecture are about functional group transformations that don't really result in carbon-carbon bond formation. However, the Grignard reaction is one of the few reactions that you'll actually learn that form carbon-carbon bonds. And it turns out there just aren't many great ways to form carbon-carbon bonds, and there's a lot of research on that. So make sure you read before coming to lab and pay very close attention to your technique, because again, even a single drop of water from any source can actually destroy this reaction for you this week and result in less than desirable results.